Welcome viewers. In this video, we'll see the performance of the RL series circuit. When the resistance, pure resistance and pure inductance is connected in series, is called the RL series circuit energized by the AC supply voltage. We are going to analyze the performance of this circuit, RL circuit. What is the voltage equation for voltage, current, phase angle between voltage and current, power triangle, impedance triangle, power factor. These things we are going to analyze in this RL series circuit. So in this RL series circuit, this R and L is connected in series, energized by the AC supply voltage. It's a current I. Because of series circuit, the same current is flowing through R as well as L. The current flowing through the R and L is same current is flowing. Now we'll consider this V equal to Vm sin omega t, applied voltage. So I is the effective value at any instant. Small I is the circuit current at any instant. Vr is the potential difference across the resistor R. VL is the potential difference across the inductor L. F is the frequency of the applied voltage. Right? Now we'll go to the analysis. The same current I is flowing through the resistor as well as inductor. So we can take current as a reference vector. Current is taken as reference vector. So based on that, the voltage across the resistor VR equal to I into R. V equal to IR. That is in phase with the current, because in the resistor always the current and voltage are in phase. Similarly, the voltage across the inductor VL equal to I into XL. XL is nothing but the reactance, inductive reactance. For inductor, always the leading the current by 90 degree. That is, current is lagging. It means the voltage is leading the current by 90 degree. The resistor always voltage and current are in phase. But in case of inductor, the current is lagging. In other words, the voltage is leading the current by 90 degree. So based on that, we have the phasor diagram is available. So this is the reference vector, current vector. The voltage across the resistor R, VR equal to I into R, that is in phase with the current, so that it is drawn in the horizontal. Then VL, voltage across the inductor I into XL, that is 90 degree leading, right? So that it is drawn in a vertical line, 90 degree leading. This indicates 90 degree leading. So this is the voltage drop across resistor in phase with the current. Voltage drop across the inductor 90 degree leading with the current. So sum of these two, vector sum of these two is nothing but the total voltage V. That is I into Z. Z is nothing but impedance. Impedance is nothing but the sum of resistor and inductance, capacitive reactance. So this is the voltage across resistor. So voltage across inductor. So sum of these two is the total voltage V, that is I into Z, that is Z is nothing but the impedance. So from this diagram, phasor diagram, we can go for the further analysis. So the total voltage V equal to VR plus VL. Voltage drop across resistor and inductor. So V equal to I into R plus J I into XL. What is this J? The J represents the voltage is leading the current by 90 degree. The J represents the 90 degree. The J operator that indicates the leading by 90 degree. So we can take I outside, so that R plus JXL, bring the I in the denominator. So V by I equal to R plus JXL. So this V by I is nothing but the impedance. V by I. So V by I is normally the resistance R. Here we have resistance as well as inductive reactance. So combinedly where it is termed as the impedance. So impedance equal to R plus JXL. So for this circuit, the impedance is R plus JXL. Right? So that is nothing but V by I is taken as a impedance. Then the magnitude of the impedance, Z equal to modulus of Z equal to square root of R square plus XL square. So this is nothing but the impedance, the magnitude of the impedance. Now this is nothing but there are two forms available, rectangular form and the polar form. We'll see that. For that we need an angle. So from this diagram, from this phasor diagram, we can calculate the tan pi. Tan pi equal to opposite side by adjacent side. IXL divided by IR. So II got cancelled, XL by R. So pi equal to tan inverse XL by R. The angle between the voltage drop across resistor and inductor is nothing but tan inverse XL by R. Now we can represent the impedance in two different forms. Z equal to R plus JXL is a rectangular form. Z equal to magnitude of Z and angle pi. This is the polar form. So we can represent the impedance in two different forms, rectangular form and polar form. This Z can be calculated from this formula, pi can be calculated from this formula. Now we'll go for the phase angle between the current and voltage. Now we'll see as per the property of the series circuit, the voltage can be written as V of t equal to VR of t plus VL of t. That is total voltage equal to voltage drop across resistor plus voltage drop across inductor. Right? This is another format. In order to analyze the phase angle between current and voltage, again we are analyzing this voltage. So VR is nothing but R into I of t. V equal to IR. Similarly, the voltage across the inductor is L di by dt. Now we know that I of t is nothing but Im sin omega t. That is for a resistive circuit in phase with the voltage. So I of t equal to Im sin omega t. So di by d of t, differentiate on both the side. Im sin omega t, differentiation of sin omega t is cos omega t into omega. So that is omega Im cos omega t di by dt. That is equal to omega Im sin omega t plus pi by 2. This cos omega to omega t can be written as sin omega t plus pi by 2. Now we got the expression for this di of t divided by dt as well as I of t is available. Now we can substitute these two values in the equation 1. This I of t and di of t can be replaced with this expression. So substitute I of t and di of t in the equation 1, so that V of t equal to Rim sin omega t plus L omega Im sin omega t plus pi by 2. So that is can be written as Rim sin omega t. This omega into Im, omega into L is nothing but XL, inductive reactance. So Im into XL sin omega t plus pi by 2. Now we got the two terms, term 1 and term 2. Now we can analyze these two terms. So the first term is the represent the applied voltage and voltage across the resistor. This term refer the voltage across the resistor. See, the phase angle is omega t only. So the current value also omega t, the voltage also we got omega t. So it is in phase with each other. The voltage across the resistor is in phase with the current. But in case of the second term, voltage across the inductor, we have omega t plus pi by 2. The plus pi by 2 is available. So the second term in the above equation is compared with the equation 1. The phase difference of pi by 2 or 90 degrees available. There is a phase difference of pi by 2 or 90 degree between this voltage and current. So it is obtained by rotating VL vector 90 degree in the vector diagram. So due to that only we are getting the 90 degree. The voltage across resistor and voltage across inductor differ by 90 degree. So that is integrated by this equation. So based on that we can draw the waveform. So this is the voltage. It starts at 0 degree. So the inductive circuit, the current is lagging or voltage is leading. So current starts after pi. Approximately if it is pi by 2 means it is pi by 2 degrees pi. After pi only the current starts. So there is a phase difference of pi between current and voltage, that is current is lagging the voltage. So based on that we can write the waveform V equal to Vm sin omega t. but I equal to Im sin omega t minus pi. This minus pi indicates the current starts after the voltage with an angle of pi. So that is indicated by omega t minus pi. Right? So we got the waveform. Current and voltage is clearly indicated. Current is lagging the voltage by an angle of pi. That is indicated in the equation. Now we'll go for the impedance. So we'll find the impedance for this RL circuit. The impedance is nothing but opposition of circuit to flow of alternating current. It is very similar to resistance. Here we have inductor is available. So inductance, inductive reactance and resistance combined is known as the impedance. So it is denoted by Z. So how it is represented by the triangle is a resistor. That is in phase with the current. 0 degree in phase with the current. This inductive reactance is 90 degree. There is a phase difference of 90 degree between the R and XL. So sum of these two, resistance and inductive drop, is nothing but a impedance. So impedance is the vector sum of resistance plus inductive reactance. So there is a 90 degree phase shift between the resistor and inductive reactance. So from this diagram we can find the value of sin pi. So this is the angle pi. Sin pi is nothing but opposite side by adjacent side. XL divided by Z. We cross multiply this so that XL equal to Z into sin pi. So we can find the XL by using this formula, Z sin pi. Then find the cos pi. Cos pi equal to adjacent side by hypotenuse. R divided by Z. Cross multiply this so that R equal to Z cos pi. So we can find the R value by using this expression. Similarly, XL value from this expression. Now we'll find the impedance. What is the expression for impedance? So impedance is R plus JXL, that we already discussed. R plus JXL is the impedance in a rectangular form. Then modulus Z angle pi is the polar form. How will you find this modulus of Z magnitude? That is square root of R square plus XL square. Then how will you find the angle pi? Tan inverse XL by R. Right? So the impedance can be represented in the two different form. One is rectangular form, another one polar form. In this polar form, this magnitude angle can be calculated from this formula. Now we'll go to the power triangle. So in the power triangle, we have real power at the reference vector, real power. This reactive power, that is quadrature with the real power, that is 90 degree. The sum of real power and reactive power is the apparent power. This apparent power is nothing but vector sum of real power and reactive power. This real power is represented kilowatt. Reactive power represented kVAR. The sum of these two is nothing but apparent power, that is represented kVA. Now we'll see what is real power, reactive power one by one. So this is the triangle, power triangle. So S equal to square root of P square plus Q square. This is the S. That is equal to S square equal to P square plus Q square. So S equal to square root of P square plus Q square. Another form we can represent, S is represented kVA, that is equal to square root of P is represented kilowatt, Q is represented kVAR. So kVA equal to square root of kilowatt square plus kVAR square. So this is a power triangle. Here 90 degrees between real power and reactive power. Now we'll see what is mean by apparent power, what is mean by real power, reactive power one by one. So the real power is nothing but the product of RMS value of voltage and current. Simply V into I. RMS value of voltage. V into I is nothing but a apparent power. The unit is kVA. What is real power? It is the product of applied voltage and active component of the circuit. There is two components available, active and reactive. So if you multiply the active component of current with voltage, that is called a real power or active power. That is nothing but, and another form, the power which is actually consumed or utilized in an AC circuit is called a active power. The given power is consumed or actually utilized by the circuit is called a AC, is called a real power. Another power is available, this is reactive power, that will be dropped in the, that will be reacted in the circuit. That's why it is called a, the power that is consumed for the, for energy conversion, consumed or utilized. So that is represented P equal to VI cos pi. The unit is kilowatt, right? So this is the active component that is actually consumed in the circuit. Then what about the reactive power? It is defined as the product of applied voltage and reactive component of the current. What is reactive component? Power which flow back or forth. That means it moves in the direction in the circuit, react upon itself, react. So the some power is required to activate, that is called a reactive power. The power actually consumed is a active power. The power actually required to activate the circuit is called a reactive power. That's why it is called a reactive component or active component. So Q equal to VI sin pi. The unit is kVAR. So there are three power available: real power and reactive power. Sum of these two is nothing but a apparent power. Now we'll go to the power factor. So power factor is the ratio of real power to apparent power. Real power or true power. What is true power? Real power VI cos pi. What is apparent power? VI. So VI got cancelled. It is cos pi. So power factor is nothing but cos of angle pi. What is this pi? Is the angle between current and voltage. So power factor will give the cos of angle between current and voltage. For getting better result, the angle between current and voltage should be 0. So if it is 0 means the power factor will be 1. Right? So power factor is nothing but cos of angle between current and voltage. It is also defined in another form. Cos pi can be also calculated from the triangle, from the impedance triangle, R divided by Z. Right? It is also called as R divided by Z. So power factor is nothing but cos pi. That is nothing but pi is the angle between supply voltage and current. So in this video we discuss about RL series circuit. Resistor and inductor is connected in series. What is the behavior of the circuit with respect to voltage, current, phase angle, impedance, power factor, power triangle and other related terms. Thank you.